Thank you so much for giving me the opportunity to present from Northeast Pennsylvania. So this is the title I have in the program. I haven't changed the talk, but I wish I had given this title instead. It's shorter and more descriptive. Because here's the thing, we've got to this date 500 known DAVs and 15 known DBVs. And yet we still lack a pipeline. So there was some work done by Barbara and Kepler in fitting a vast number of DAVs. They did 83 of them, if I'm not wrong. But when you do this kind of work, you really need to have some assumptions. And there's a set of problems that we run into when we try to fit many stars at once. One problem is to find a parameterization that works for every star. Another one is mode identification. JJ gave a great introduction to that, and also in a couple talks we had some keys on how to do some of that. But for most stars, we're going in, we don't have mode identification. And JJ mentioned this, but did not want to touch it, the issue of uniqueness of solution. So I'm going to talk about that. So as a brief background on parameterization, I'm doing my work with the White Dwarf evolution code, WDEC, and the parameterization that I do is I don't want to call it standard. I do it differently, but you've seen those profiles already today. So there is, just to summarize, mass and effective temperature are parameters. And then there's a set of parameters that have to do with the envelope being the helium and the hydrogen in the model. And then there's a set of parameters that have to do with the core, the oxygen and carbon rich part of the model. So knowing, and all in all, with WDEC, that's 15 parameters. And that's computationally, first of all, difficult to handle. And also, for most white dwarfs, we only have a few to half a dozen modes. A dozen if you're lucky. So 15 parameters is too many to vary. So one thing to do or that I do when I approach fitting of a star is, the first thing I do is to try and determine, okay, which parameters out of those 15 matter most. So here's an example of such a numerical experiment. Here I was attempting to look at a DAV called R548. And I work with grids. So I took a model on the grid that had periods that matched R548 reasonably well, had a similar type of period structure. And then that particular grid model has 15 parameters associated with it. And then I vary one parameter at a time, and I watch what that does to the quality of the fit. The quality of the fit is the departure from the pairs of the fiducial model. So here is the fiducial model, and then I depart from that. And then looking at this, I qualitatively bin that into 3 bins. So I looked at some parameters that I know do nothing. So if you must know, these have to do with the envelope, and those are some of the envelope parameters, and this is the efficiency of convection for R548 does not come into play. So I have that. I know that I don't need to worry about these. And then I have some that do seem to matter a lot, like the effective temperature, the mass, the location of the thickness of the hydrogen layer. And then I got things that are in between. So this is a 1. This is a, in between is 2, and then don't matter is a 3. And I color-coded this to make it easier to see. So here's R548 and the 15 parameters and that classification. And then I went and I looked at more DAVs because we want to know are there parameters that we can discard, for instance? Very useful to know. So I did 12 more. And then I find that consistently those particular 3 parameters really, you don't need to put them in the fit. So great, we're down to 13, 12. And then we know over here, effective mass temperature and some envelope parameters matter almost every time. And those are traditionally the ones that we've used. And there's a reason for that. I think people have known that intuitively by doing many fittings. But the problem I'm having here is with the core. The core is a Christmas tree. For some stars, some of the core parameters matter. For some stars, very little. So what do? Do you model the core or not? So ideally, you would want to do that for each star, but it's very time consuming. So if we're thinking of doing a pipeline fitting, it'd be good to have a faster method. So there has been some discussion today about that, or questions anyway that were asked. So it is true that there is some rule of thumbs and things we know from doing astroseismic fitting with G modes. We know, for instance, that the lower period modes tend to be sensitive. They penetrate deeper in the core, so they allow us to, they should be sensitive to core structure. Longer period modes, we expect them to be less sensitive to core structure. But it is not that simple. There's I think what I've just shown and more work, I'm just citing some work here that I did, but we know it's not that simple. You can't just use that rule of thumb. But we expect that there should be a relationship between the structure of the period spectrum, what periods are in there, and whether we're sensitive to the core or not. So but we need to be finer in that mapping than just the rule of thumb. So that's work that I think needs to be done. And then there's the problem of the uniqueness solution and the L identification, and they go hand in hand. So I'm going to discuss them together. And we get families of solutions because even when you vary a limited number of parameters, like I said, many times we only have a few periods. So very often in white dwarf seismology, we don't get a unique solution. One handle we have on this is that in the mass effective temperature plane, we have external constraints, and a lot of us in the field have been using that, or try anyway. So one is the spectroscopy, but that has its challenges. But now with distances, we have this an extra constraint there that is great to use. So what I like to use is what's called the Gaia lines. And so I put these down in the mass effective temperature plane. They're built from pure Astro 101 using the Gaia parallaxes, the log G from spectroscopy, and then a mass radius relationship. The advantage is that we don't need the effective temperature. That's often a problematic thing with spectroscopy. And to get those lines, I do carry the error bars that we have in the parallax and the log G, so I'm going to get actually a range. And for the mass radius relationship, I use the WDEC. It's good because I also use the WDEC to do the fitting, so that's at least self-consistent. And right now I'm doing something pretty simple where to get the mass radius relationship, I just picked a fiducial model with a given internal structure, but I do take into account a temperature dependence when I use the mass radius relationship. So here's an example of that work with a particular DAV, EC23487. And those are I apologize about the color scheme. I did not think this through. So we have the two Gaia lines here. We have that region that is I described. I also put down on this plot boxes this is the spectroscopy. So for this particular star, we have 3 different determinations. It's a small box, but that's also a determination. And you start to see kind of the problem we're having with using spectroscopic constraints. If you're lucky, if it's a well-studied star, you can get spectroscopic boxes that span the instability strip. So perhaps here, for this particular star, we can maybe draw a box here conservatively. And so then we start to get, there's an overlapping region here. You could argue, at least we're trying to get a handle. And then what I've also plotted on here, the color mapping. This is a result of a period by period fit to the pairs of EC23487, with dark blue being the best fit. And the location of this dot is where the best fit model is. So this is a case where it's not too bad. But what can we do? What if we want to line all of this up? Like, for instance, I'd be happier if this lined up with Gaia lines, for instance. And for some stars, it's worse. Like, you can be really far off of those constraints. So how can we line things up a little better?
Agnes, you have 3 minutes.
Thank you. Perfect. I think I can make it. So how can we line this up a little better? So there's more parameters in there, right? Like the structure, the internal structure of the model. That does have an effect. But something that can really drastically change things around is the mode identification. So one approach to mode identification is to have it as an output of the fitting. So you try different mode identifications for the pairs in the spectrum, and then you see how good a fit you can get, and then you will choose the mode identification that gets you the very best fit. I do that. I know other people do that too. It's a fair approach, but I think it's also good to look at constraints. So when we had just spectroscopy, that was a difficult process, because when you have temperatures that span the entire instability strip, what are you supposed to believe? But I think with the distances, we are a little more confident in our constraints in the mass and effective temperature plane. So I think this can help guide the mode identifications. You pick the identifications such that your best fit models fall within the region where you would expect them to fall. So in conclusions, I hope I presented a path to improve pipeline fitting of white dwarf peer spectra, and also part of this is to increase our confidence in the accuracy of our results. The Gaia parallaxes are a key part of the process, and if we want to really do this faster, like automate, I think we really need to have a systematic mapping between what parameters matter the most and the types of peer spectra we have. So this is all I had. Thank you so much for listening.
Barbara?
Hey, Agnes. Hi, Agnes. Nice talk.
Hi.
Hi. Did you use the colors to determine log G?
No. See, I don't determine log Gs. I forgot to mention log G. I take from the spectroscopy. So whatever Janina's et al. Use, like for instance, for EC 23487 or whatever Custer used.
Hi, this is Boris. It's kind of, I would just caution spectroscopy measurements, at least for large amplitude pulsators, because whatever you see is an average of temperatures across the surface. And even a Gaia parallax then doesn't help, because you have the spectrum is kind of an intensity weighted average over the surface. And so whatever you measure may not be the true radius, but some kind of area that is temperature weighted.
Are you talking about because the G magnitude comes into play, so are you talking about that being maybe also affected?
Yes, basically you never, like effective temperature is only defined if the entire visible surface has the same temperature, which
Yeah.
for White Dwarf is not the case. And depending on where the pulsation modes are across the star, even if you average over some amount of time, that may not be a homogeneous temperature across the surface that you see.
Yeah.
I don't think that the variation on the temperature will actually affect that much the fit. Another question? No. I have a question, Agnes. As JJ showed in the morning, there are some stars that have a few modes, the short ones that we like, but there are also the cool ones that have a lot of modes and they are long, and you can lose sensibility there, especially in the core part. How do you deal with?
Yeah. So right. You're right. Though it's not quite as simple. So what is also true, so our approach needs to be different. I didn't show this here because I was focusing on the period by period fitting, and EC23487 is not one of those long.
No, yes.
So well, I'm not discounting the long period pulsators, because if they give you enough of those long period pulsations, then you can get an asymptotic period spacing. And if you have an asymptotic period spacing, then that gives you an additional constraint, and it allows you to you get lines that go the other way, and you can kind of get an
It's a different kind of data.
Yeah.
Direct fitting.
They're useful too, I think. Yeah.
Okay, so we thank Agnes again.